Hello everybody, Lara here from Theatre of Science. It's lesson 5. I can't believe we're here already of our iGCSE journey online. Lesson 5 of forces in motion. Needs to do quite a lot of recapping because this lesson is on resultant forces, but it beautifully sort of feeds into everything we've done so far. So, we've looked at vectors and scalars, right? Let's talk about that a little bit. You remember the difference between a vector and a scalar? Can you give some examples? If you can, you've probably already got a mark at iGCSE. Oh wait, it's YouTube and I have to write backwards. Yay, go YouTube and your amazing technology. Scalar, I can't spell forwards now. Scalars and vectors. So scalars, did you name a couple? You could have had distance or speed. They're the ones we've looked at so far. They can be described with just a number and a unit. How fast are we going? 5 meters per second. Correct. Vectors have also got to have a direction. So displacement is like direction, but it's a scalar. So if you were talking about your displacement, you'd have to say 5 meters to the left or to the east, right? Or we've looked at how velocity is a vector. Velocity is like speed, but also in a direction. So last week we learned my favourite thing, that something being spun round in a circle is moving at a constant speed, but it's changing velocity because its direction is changing all the time. Like first it's going that way, then that way, then that way, and that way. Yeah. So so accelerating means something changing its velocity. So something moving in a circle is changing its velocity. Okay, right. So first question, we've been looking at forces. The force, like your weight, how much the force of gravity is pulling you down to the ground. A force is a push or a pull. It's measured in newtons. Do you think that a force, a push or a pull, is a scalar or a vector? Some of you might have been doing some reading on your own time and already know this. Is it a scalar or a vector? I'll give you 10 seconds to decide. Is force a scalar or a vector? And then I'll give you a clue. Now you've got 8 seconds. 5, 4, 3. Come on. There's a lot of writing on this. There's not. All right, your clue is... That was fun. I'm going to do it again. You ready? Watch carefully. This is your clue. Well done if you said it's a vector. Yeah. Forces have direction, don't they? We spent all last lesson drawing force diagrams like this. Arrows moving in different directions. Direction is incredibly important. So well done. Yes, force is a vector. That will come up today. That's not my board rubber. Its bottom is not fluffy enough. Another recap, right? We looked at Newton's first law. Newton's first law says that if the forces acting on something are balanced, then if it's still, it'll stay still, right? So you get a pen that's not moving. If you push it with an equal force on both sides, you can push with loads of force. It doesn't actually move because the forces on it are balanced. If you pushed it with a little bit more force one way, then it would obviously move. And when we learned the really weird thing that if something is moving and the forces on it are balanced, then it keeps moving. I'm holding my arm out because, imagine Abby's going to get cross with this because she's always like, there are some particles in space. It's not how she speaks. But anyway, Abby, if you're watching, we're just going to pretend that space is an absolutely perfect, frictionless place. You push a pen in space and you take your finger off the pen, and we've looked at how as soon as your finger is removed, there's no force pushing the pen along, okay? Force doesn't linger. The force is gone now. But what happens? There's no air particles or anything pushing back on the pen. So there's no force pushing the pen in this direction, but there's no force like friction or air resistance or whatever slowing the pen down in this direction. So you push a pen in space, it just keeps going. So if the forces on a moving object are balanced, it'll just keep moving at a constant speed forever. Right, which leads us nicely to the subject of this lesson, which is Newton's third law. Newton's third law, you'll have heard this one already, is basically for every action there is an equal and opposite reaction. We've kind of already looked at this. So you are presumably sitting in a chair. You might be standing up. Either is fine. We've looked at how everything has a weight, right? Everything has mass and force is pulling that mass down and towards the earth, and we call that weight. And we've also looked at how this is not a balanced force diagram. There's an unbalanced force acting on this. So this thing is presumably accelerating through the floor. Why are we not accelerating through the floor? Because the forces on us are balanced. For every action, there is an equal and opposite reaction force. So we push down on the chair, and the chair pushes up on us. And that is it's what we call a Newton's third law pair, okay? For every action, there is an equal and opposite reaction. So if I grab stuff now, like this Play-Doh and a mug, then my weight is slightly increased. I'm pushing down on the chair more, but I still don't go through the chair, do I? Because the chair pushes back with a force that is equal and opposite. It's going in the opposite direction and it's the same size, so it's balanced out. Obviously, there would come a point where I could gather so many things that my weight would be more than the chair could stand and the chair would break. But until then, it's like anything, like push on the wall or push on the table. The harder you push, the more it pushes back. For every action, there's an equal and opposite reaction. So let's get on to octopuses, because I said to bring a washing up bowl if you had it, and a sort of squeezy plastic bottle that will fit inside the washing up bowl. So we need to talk about how octopuses are jet propelled. We also need to talk about, because lots of people have been criticising me for this, the plural of octopus is octopuses, because it's a Greek word. One of you guys told me this ages ago. It's a Greek word. If it's a Latin word, you put an I on the end. If it's a Greek word, then you don't. So there. Right, get your washing up bowl, get a plastic bottle, and this is how an octopus works, right? Exactly the same. This is its mantle. It's got just a kind of sac inside its body. And obviously the octopus is in water, so it fills the mantle up with water. And then when the octopus wants to move, what it does is it squeezes out the water. I'm going to drop more water in here. And all I'm going to do to this plastic bottle, if you haven't got this, by the way, it's a bit faffy, isn't it? Just go through the recycling but next time you have a bath and do it in the bath. It's really good, honestly. What I'm going to do to this plastic bottle is I'm just going to squeeze inwards like this and see what happens. Now it's full of water. You ready? Hey! Let's do it again. Give it a good hard squeeze. It's got to be full of water. I promise you, I'm not dragging it backwards. I'm just squeezing inwards. But our octopus is being propelled forwards, isn't it? We have to pretend that the eyes are on the bottom here and that this hole is like its bottom. It's not its bottom, it's a siphon, but I'm not a biology teacher. What happens? Why is this bottle moving? Why is the bottle being pushed backwards? Using this idea of Newton's third law, for every action there is an equal and opposite reaction. Let's use a better word than moving for a start. What is the bottle doing? What is the bottle doing? It's going from still to moving. So it's, yes, correct, it's accelerating. So we've applied a force and we've got an acceleration. But why is it moving that way? I'm only squeezing in this direction. So obviously my squeeze in this direction is causing the bottle to move in that direction, because you can see it's crumpled, it's changed shape. That's what forces do. But why is it moving backwards? I don't know why I just keep saying that question to you. I actually want you to answer it. Let's come back over here and I'll show you. Should I just... I was giving people loads of explanations yesterday. Yeah, we probably had better go through it, haven't we? That's a lot. Oh no, I left my Lego camera phone holder at the sink. Can't do a show without that. What is happening? Well, what's happening? I'll tell you and then I'll get you to try and write it down. The bottle is pushing on the water. Are we all okay with that? The bottle is squeezing inwards and the bottle is pushing on the water. So what must the water be doing to the bottle? If we're thinking about Newton's third law pair, we've got the bottle and water. The bottle is pushing on the water in, let's get the bottle. Here we are. So the bottle is pushing on the water in this direction, isn't it? So let's pretend this is our octopus. There's its face. So the water's pushing on the octopus in this direction, which is why it went that way, didn't it? Is that okay? The octopus pushes on the water, so the water pushes back on the octopus, and makes the octopus like accelerate, move. I'm just going to give you the question sheet now. I think you've had all you need, at least to get a bit of brain exercise, and then we'll go through the answer. Here we are. Explain, please, by talking about the forces acting on an octopus, how it moves forward. So I've given you the first part of the sentence. An octopus fills its body with water, then what happens? And I've put these words might help. Can you use all these words? Equal, opposite, force, forwards, and Newton's third law. Question 2 might actually help you with question 1. Draw a force diagram of all the forces acting on the octopus. And remember to show larger forces with longer arrows. Just remembered, I just realised that the last couple of lessons I think I haven't done that. And question 3 is for people who are feeling well confident. This is really tough. It's a classic puzzle. You push a ball, but according to Newton's third law that I've just told you, the ball pushes back with an equal and opposite force. So doesn't that mean the forces are balanced? So why does the ball move? Explain, or attempt to explain. Usually, like in home ed, I say, say it out loud or write it down. For this, if you're planning to do iGCSE physics, unless you've got some kind of arrangement where you don't write, it would be very useful to write it down, because then you can look at the answer and you can improve it, and that's how we'll get you passing your exams. I'm going to do something I don't normally do. I'm going to be quiet for 1 whole minute. Surely that's been a minute. How are you doing? I don't give you much time, do I? And it is iGCSE, so you do need to exercise your brains on this one. Even the force diagram of the octopus, like I say, I've done it twice now on my Facebook lessons, and I've realised that I didn't think about a couple of things I should have done. And question 3 is right tough, isn't it? All right, 20 more seconds. 15. 10. Okay, right, come on. How'd you get on? I should have been writing the sentence myself, shouldn't I? So a lot of people on Facebook were writing things like, the octopus pushes the water out and so it moves forward. But come on, this is GCSE. We need to use precise wording. So I think what I would say is an octopus fills its body with water, then pushes the water out in the, I'm going to say in the backwards direction, because it's going to help me to say why it goes forwards. The octopus pushes the water out in the backwards direction. The water pushes back. How does it push back? With a force that is equal and opposite. And it's opposite. So if it's pushed the water out backwards, if the force is opposite, I'll put so octopus moves forward. I'll just put oct moves forward. And then you were supposed to include the phrase Newton's third law, weren't you? I'll just add in my head, according to Newton's third law. The octopus pushes the water out in the backwards direction. The water pushes back with a force that is equal and opposite, so the octopus moves forward, according to Newton's third law. I'm happy with that. It'll probably help to draw a force diagram. It'll definitely help with question 3 to draw a force diagram. So you drew a dot for the octopus, well done. The octopus has weight. It's kind of a weird misconception that we're weightless in water. Gravity still works in water, so the water is pulling the octopus down. But the octopus isn't sinking down, is it? Because, well done if you got the word up thrust, if you'd been doing some extra reading. But you could have said just the force of the water pushing the octopus up. Strictly speaking, that is up thrust, so I'll put up thrust. Well done if you knew that the octopus had weight, and you didn't get this one, but you knew there must be something there, because obviously the octopus is isn't moving, is it up or down? It's staying still in the vertical direction. So weight pulling it down, up thrust, just like the push of the water particles, keeping upwards. And then, right, so we need to think about the forces that the octopus is experiencing. So the octopus pushes on the water, but what is pushing or pulling on the octopus? Weight is, up thrust is, and the water is. So I'm going to draw, what I did last week, or yesterday, is I drew that push of water. Oh, sorry. Oh no, I've written up thrust backwards as well. It's very difficult to remember when to write forwards and when to write backwards. Why is that not quite right, what I've written there? Or what I've drawn there? Why is that not quite right? If this was a 1, 2, 3, if this was a 4-mark iGCSE question, which it might be if you're lucky, if it was a 4-mark iGCSE question, I reckon I've got 3 marks for that. Why have I not got 4? 5 seconds. 4, 3. Oh, actually, wait. No, it's probably fine. Do you know what I was thinking? I was thinking that this arrow needed to be longer. But that's silly, isn't it? This arrow, the push of the water, doesn't need to be bigger than the weight or the up thrust. Yeah, that was quite silly, but a good learning moment. These forces are balanced out, so the octopus isn't moving up or down. So it wouldn't matter if the push of the water was teeny tiny, would it? Because this force is kind of balanced by this force and there's nothing there. So this side would still win, if you know what I mean. Do you get what I'm saying? I was thinking, oh, the push of the water needs to be like the biggest, longest arrow because it's going that way, but that's not true. A thing doing this is still moving, you can't see it very well, but a thing doing that is still moving that way. It's not accelerating as much as something doing that, but as long as there's an arrow in that direction and it's bigger than the arrow in that direction, it's still going that way. Okay, thanks guys, thanks for helping me think through that. Question 3, well done if you thought about this. What's going on? I've got this Play-Doh. If I push on the Play-Doh, then the Play-Doh pushes back on me with a force that is equal and opposite. So why does the Play-Doh move? If this Play-Doh is still and we apply balanced forces, we've just learned that if something's still and the forces on it are balanced, then it stays still. So what's going on? The trick is you need to think about the forces acting on the Play-Doh. So I am pushing on the Play-Doh. I'm pushing on the Play-Doh. That's a force that the Play-Doh is feeling. The Play-Doh is pushing back on me, but that's a force acting on me. So you need to, it always helps me to draw a force diagram. If you draw a force diagram, then what is the Play-Doh experiencing? It's experiencing the push of my finger, my push. And that's the only force it's experiencing, okay? The force of the Play-Doh pushing on me, that's my force diagram, that's somewhere else, and maybe that would be balanced by like the muscles in my hand. So only think about the forces acting on the thing that is the subject, if you know what I mean. Is that okay? That's the only thing that helps me. Just draw a force diagram, what are the forces acting on the thing. Okay, well done. Right. I said we were talking about resultant forces, so we keep saying balanced and unbalanced forces. A nicer way to talk about it is the resultant force. So I think the easiest way to tell you what resultant force is to give you this question and make you think it for yourself. So it's a classic scenario, we've all been there. You find a massive biscuit in the street. It's a very robust biscuit. It's not going to break. You see it at the same time as your friend. So you start pulling with a force of 6 newtons and your friend starts pulling on the other side with a force of 4 newtons. Who wins the biscuit? That's fairly obvious, isn't it? I asked my 6-year-old yesterday and he got that straight away. Who gets the biscuit and what overall force is acting on the biscuit? That's the harder question. What overall force? Another word for overall force is resultant force, or what force does the biscuit effectively feel? What to the biscuit, what's happening? My 6-year-old got that wrong, but then I gave him a clue and he got it right. So let's see if the same thing happens to you. So first off, who gets the biscuit? I imagine that you're all saying, well done, that the person pulling with a force of 6 newtons is going to win the biscuit, yeah? The forces aren't balanced. If it was 4 and 4, we've learned the biscuit would stay still. But if it's 6 newtons on this side, then the person here is going to win the biscuit. What's the overall force acting on the biscuit? A lot of people in the Facebook lesson, and indeed my 6-year-old yesterday, said that the overall force would be 10. That is not correct. That would not be the resultant overall force on this biscuit. But if I tell you that it's not 10, can you see what else it might be? 5, 4, 3. Think about if it was 4 and 4, what force would the biscuit be experiencing? Yeah. So the overall force on the biscuit is 2 newtons. Because force has direction, these 4 newtons and 4 newtons on this side sort of cancel out. I shouldn't have used a biscuit because the biscuit is all crumbly. Imagine that it's just a massive sturdy block of steel. If 2 people are pulling on a block of steel with a force of 4 newtons each, the block of steel kind of doesn't feel anything, does it? If 2 people are pulling with like 100 newtons each, a steel's not going anywhere. If one person pulls with the force of 100 newtons and one person pulls with the force of 101 newtons, the steel block is going to move as if there's just a 1 newton force acting on it. Do you see what I mean? You've got a steel block, 100 newtons on one side, 101 on the other side. It would behave in the same way as if just one person was on one side pulling with a force of 1 newton. Is that all right? So the resultant force is like the overall force acting. It's like kind of the force that the thing actually experiences, okay? It's kind of simpler, really, once you get the hang of it. So I've got you some questions here. With pleasant pictures of things like hedgehogs and balloons to make this fun and not awful. I've done you an example as well, so that should help. For each of these situations, please, I'd like you to say what the resultant force is and draw an arrow to show the direction that it is acting. So here's your example, okay? Probably worth thinking about this first of all. You've got a ball which is just starting to fall off a cliff. So it's got a force of 10 newtons pulling it down and 5 newtons, presumably air resistance, air particles bashing off it, 5 newtons pushing it up. So the resultant force is that 10 newtons minus the 5 newtons, because like the 5 going up and 5 going down cancel each other out, yeah? So the resultant force is 5 newtons down, 5 newtons in the downwards direction. Is that okay? See how you get on. So you've got a trolley, which is being pulled forward with a force of 15 newtons, but also being pushed back with a force of 10 newtons. What's the resultant force on that in the direction? A hedgehog with 8 newtons being applied to the left and 2 newtons being applied to the right. A balloon with 50 newtons being applied upwards and 20 newtons being applied downwards. A sledge with 5 newtons on either side. A cat on ice. It's a great BBC show, isn't it? With 20 newtons being applied to the left and nothing on the right. And question 2, they're supposed to get harder. Question 2 is got 2 arrows on the right, a 6 newton and a 2 newton, and just 1 arrow on the left, which is 1 newton. And question 3, which is tough and has to make you think back on other lessons. Describe how the objects could be moving. Could they be staying still, speeding up, slowing down, moving forwards, moving backwards? There's more than one choice for each. Hopefully that will bend your brain a little bit. And if you've got any questions, don't forget that on my Facebook page, there's a little post saying, I'm on YouTube right now, but if you want to comment or ask me questions, comment on this post. So you can always go over there. Writing backwards again. Shall I go through the first twos just so you know you're on the right track? So if the trolley is going forwards with a force of 15 and backwards with a force of 10, the resultant force on it, well, that 10 would balance out the 10 on the other side. And the resultant force is 5 newtons in the direction of the 15 newtons. That's the resultant force. It's not necessarily the direction the trolley is travelling in. We'll talk about that in a sec. And the hedgehog, you've got 8 on one side and 2 on the other side, so the 2 and the 2 cancel out. The 8 take away 2 is 6 newtons in the left hand direction, and the balloon is going up with a force of 30 newtons. Okay, I'll give you another like 3/4 of a minute to get those done. Okay, should we go through the rest? The sledge, what's happening to the sledge? What's the resultant force? The resultant force on the sledge is 0. So when we've been saying the forces on something are balanced, a nicer way of saying that are that the resultant force is 0. There's no overall force acting on it. It's balanced. So there's no direction. It's balanced. Cat on ice, the resultant force there is 20 newtons, and the direction is in the direction of the 20 newtons. Question number 2, I hope this didn't catch you out. So these two forces, the 6 newtons and the 2 newtons, they're both pulling in the same direction. So we can just add them together to make 8. And then you've got 1 newton pulling on the other side. So you do 8, take away that 1. So it's 7 newtons. Well done if you got that. If you didn't, then I hadn't taught you it, but you know now. Describe how each of the objects, 1 to 5, could be moving. I was quite pleased with that. I like thinking about this. I find it quite mind-bending. Let's have a look. So I will go back to that sheet if you want to write the answers down in a sec. So that's for a bit later. Yeah, let's think about our force diagrams again. You remember last week, let's say we've got a ball on the ground. Do you remember me saying that, let's make the ball a bit bigger because you're quite far away. When my finger is pushing the ball, the force diagram for the ball looks like that, okay? There's a push in that direction, my finger pushing. As soon as so you could look at this force diagram and think, okay, the ball is moving in that direction. As soon as I take my finger away, like we say, pushes don't hang around, do they? So there's now 0 force acting in that direction. But we've looked at how there is a force pushing back on the ball, the force of friction, the friction from the floor. So now the only force acting on this ball is friction pushing it in this direction. So what is the ball doing? Well, we know, don't we? Because we've done this in real life. If you push a ball, then when you're pushing it, it's moving forward, it's accelerating. When you take your finger off, it's still moving forward, but it's slowing down. So here we've got a force diagram where there's an arrow pointing to the right, but what's happening is that the ball is actually moving to the left, but it's slowing down. It's decelerating. It's negatively accelerating. And it's negatively accelerating, slowing down because there's a force pushing it in that direction. But it's weird, isn't it? Like if I hadn't told you what this was a force diagram of and you just saw that, you'd have no way of knowing whether that thing was speeding up in that direction, in the same direction as the force, maybe someone's there pushing it, or slowing down in that direction because there's friction or air resistance or anything pushing against it. So it's the same with these guys. Like this trolley, obviously you look at it and you assume that it's moving forwards. What's probably happening is that the friction of the supermarket floor is providing 10 newtons, but you're pushing with a force of 15 newtons. So what's happening? Well, careful, it's got a resultant force on it. So it's not travelling at a constant speed, it must be accelerating. You're pushing a bit harder than friction, so you're speeding it up. But of course, I haven't said that it's moving in that direction. The resultant force is acting in that direction, but what might be happening is that you might be pushing it backwards with a force of 10 newtons, and the friction pushing against you might be 15 newtons, and the trolley might be slowing down to the left. That's just the kind of trick they're going to try and pull at iGCSE to check your understanding. Same with this hedgehog. The assumption is, isn't it, that it's rolling to the left because the resultant force is 6 newtons to the left. But it could be slowing down as it rolls to the right. It could have some friction acting on it. Same with the balloon. I don't want to, this is making my brain bend too much. Why would a balloon be falling? Why would the overall resultant force on a balloon be 30 newtons upwards, but it be falling? I guess well, it can't be plummeting to the ground because it's slowing down. Oh, I guess this is a kind of parachute situation, isn't it? Yeah. So you've got a lot of lift. Yeah. So the balloon would be moving downwards, like a parachute moves downwards, but the resultant force is in the upwards direction because, if you jump out of a plane with a parachute, you very much hope that you are going to slow down before it hit the ground. Okay, thanks, guys. I really think it's taken 3 lessons, but I'm really thinking this through. The sledge, hopefully you got... Oh, I just realised I've actually written these in, sorry. So trolley could be speeding up forwards or backwards. Hedgehog could be speeding up or slowing down, as could the balloon. The sledge, hopefully you got, it could be still... or it could be moving at a constant speed. Be careful, it has to be moving at a constant speed or still. It's not accelerating because the forces on it are balanced. No resultant force. Cat on ice could be speeding up or slowing down, and that's as far as I went. Right, is that okay? Can you come back up here? So we've talked about Newton's first law last week. The idea that if the forces on something are balanced, it stays still or it keeps moving. We've just done Newton's third law. For every reaction, there is an equal opposite reaction. Forces come in pairs. We've got to talk very quickly about Newton's second law, haven't we? Just, just got to do it. It would be rude not to. So Newton's second law, we'll come on to it a bit when we talk about momentum later on, but you can at GCSE, quite often we describe Newton's second law as force is equal to the mass of something times the acceleration of something. You might have come across this. You might be feeling like a proper physics student now. It's F equals ma. Have you heard of that equation? The important thing to note about this equation is that this force they're talking about is the resultant force, the overall force. Okay? Which kind of makes sense. So I think rearranging it and talking about rockets is the nicest way to make this make sense. So if F equals m times a, what does a equal? Like I say, I think we'll do a whole maths lesson later, or I'll point you towards some good resources. I don't like teaching maths online because you're all at such different levels. But a is equal to F divided by m. You're all right with dividing, aren't you? So if you've got loads of sweets and you share them out between a certain amount of people, everyone gets a certain amount of sweets each. Is that all right? So if you've got loads of sweets on the top here and you share them out between not many people, if F is big and m is very small, A is big, isn't it? You've got loads of sweets, not many people, everyone gets loads of sweets each. If F is small, not many sweets, and m is big, loads of people, no one gets very many sweets each. So it's the same in this case. The bigger F is, the bigger A is. The smaller m is, the smaller A is. So we were just talking about Artemis 1, NASA's rocket, which is just refusing to launch. This is the reason that rockets have to have a very low a mass as possible. That's why astronauts have to eat that terrible dry food. Because the lower the mass, the more acceleration you're going to get if the force stays the same, right? You make that smaller, fewer people. You make that bigger, more sweets. And it's also why NASA attaches basically massive fireworks to the sides of its rockets to make F as big as possible. So if F is big, M is small, A will be big. It's basically Newton's second law. As usual, probably not this week actually, because this is my 40th very soon, so I'm legging it to go on a little trip with myself in a minute. But sometime over the weekend, I'll post up some links like I usually do to like YouTube videos that I think are good or internet resources that'll help you practice this, and some past paper questions as well. But I think actually we will leave it there. Oh, thanks. I feel like I've really understood some things that I hadn't understood before this lesson. I'm just going to go to my Facebook page and see if any of you have left me any messages. Oh, Chloe has sent me a message. Oh, Chloe, I hope you're not saying, have I got your letter? Because I haven't got your letter. Although the post hasn't been this morning, so I don't know. Maybe you're not. Maybe you're asking me a question about forces. I will see. It's coming up now. Do, 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 do. Oh no, I'm in a group. Sorry. I don't want to be in my group. Man, Facebook's confusing, isn't it? Here we are. Oh, I didn't say if you're not supporting me and you want to, then you can. Thank you, that'd be great. I'm about to post out loads of these actually. This is Theatre of Science magazine. If you support me with £5 or £6 a month, there's enough people doing that. Legends. That I can do this lesson and a home ed lesson and a show with a Lego story time every week. And posting Theatre of Science magazine. So the next one's due back from the printers in postal strikes notwithstanding about 10 days. So, but if you sign up now, you still get the bumper issue on seeds. It's got like a free tiny sprinkle of seeds and a biodegradable plastic bag and a quiz and a beautiful comic. It's such a good magazine. I love it. It's the science magazine that I want. 2 comments. I had to faff around for. So I'm just laughing because my only comment is Chloe going, I understood some of that. Oh no, I understood some of all of that. Oh, that's brilliant. You understood some of all of that. Excellent. Hello, Chloe. Thank you for watching. And hello indeed everyone who's watching this on catch up and lurking, but not Joseph because he gets super embarrassed when I say his name. Joseph, as you were. Thanks for coming everyone. I'll see you very soon. Bye.